Good morning. Welcome to lecture 3. We're going to discuss chapter 2, which is geometrical optics, in detail in this lecture. But before we proceed to chapter 2, I'd like to discuss one of the problems on the homework that has to do with de Broglie principle. You know that the de Broglie principle states that lambda is equal to h over p, where this lambda is wavelength and p is the momentum, right? You can also write this as p is equal to h over lambda. So now let's talk a little bit about quantum mechanics. So quantum mechanics QM, it does not really deal with individual particle measurements. It rather deals with ensembles. So it's very statistical. In fact, if you have had a course on quantum, you know that in quantum mechanics, we don't compute the exact values, we rather compute expectation values or averages. So when we are talking about in problem 1 on homework 2, when we are talking about the wavelength of a tennis ball, we are modeling this macroscopic object not as a plane wave, not as a wave of single frequency. It is really a wave packet. So this should really be a wave packet, right? So this is really a wave packet. So this wave packet is obviously not composed of a single frequency or single wavelength. It is a combination of different waves. And it is, you're modeling this object like a wave packet. Nevertheless, we are talking about a single wavelength in the problem. So that's what I want to bring forth, that in reality, when we look at wave function, for example, in quantum mechanics, we are not really looking at a single wavelength. It is rather we're looking at average momentum. So here the momentum we are taking is average momentum of an ensemble or expectation value. And then from there we are coming up with a wave packet or lambda, right? So in case of electrons, for example, if I have a lanthanum hexaboride filament and electrons are emitted from it, you are again calculating the ensemble average of their momentum and coming up with a lambda or a wavelength. So don't be confused and don't treat, we are not looking at an individual particle per se. So if you look at an individual particle, this kind of wave particle duality often leads to misleading conclusions that something is both a wave and a particle at the same time, which is against the principle of non-contradiction. So the wave nature is coming from an ensemble measurement. I hope you watched the video that I sent with lecture 2, not lecture 2 itself, but there's another video of a 1 minute video of electron microscopy experiment of double slit experiment rather using electrons, where you see that a wave pattern, the fringes appear after you have made the measurement with millions of electrons. It's not a single electron, right? So that's what you need to bear in mind on de Broglie's principle. Okay, now moving on to chapter 2. So here we are going to deal with geometric optics, which means we are going to ignore the wavelength. So we are going to say, okay, lambda is 0. We're going to ignore the wavelength. That's where we're going to approximate optics as geometric optics. So in the olden days, people treated light as simply rays of light, right? Simply rays of light. Right. In fact, Newton thought these rays of light are made up of particles. So that's how he was trying to explain the observed optical phenomena. So we are going to treat for the purpose of this chapter, we are going to treat light as simply made up of rays. So that said, let's look at one of the key principles, that's the Huygens principle. So if I have one ray of light or one wave of light where I have, so this is not the same as a plane wave, this is just disturbance or one ray of light, one particle on this wave front. AB is the wave front, that is the wave we are beginning with, and each point on this wave front acts as a secondary source to create spherical waves or wavelets, which in turn propagate with the speed of light in that given medium, right? And when those wavelets are combined, you get the next wavefront, that is A prime, B prime. And notice that here V is the speed of light in that given medium. So in a given time t, this goes as far as Vt. So this wavelet would have a radius of Vt. So even if you have a spherical wave, it's the same concept. If you pick one point on this wavefront within time t, Vt is the radius of the wavelet it creates, and each point on this wavefront creates similar wavelets. And when you combine all these wavelets, you see that you have a new wavefront, A prime, B prime. Now think about it this way. For example, if I place a charge here, let's say Q, I am placing this charge there in the space, and this creates a perturbation or a disturbance in the space around it. That is the electric field. So it creates rather a very strong disturbance right around itself, right? This is very strong. So let's show that it is very strong here. So it creates a very strong disturbance. But you also know that space is not nothingness or emptiness. It is extension, right? So this part of the space where there is a lot of electric field right around the charge acts on a part of the space that is right next to it, right? So this part of the charge acts on the part of the space that is next to it, and this part of the space acts on the part that is around it, and it disturbs that, but the electric field as it goes out gets weaker, and this part of the space acts on the space around it, and electric field gets even weaker, so on and so forth. So one part of the space is acting on another part of the space, and that's how the electric field of a charge is spread, right? So it is in the same sense that essentially light is nothing but electromagnetic field. So if you take one particular point on the wavefront, the secondary wavelets that you are getting are in turn just like how one part of the space is creating disturbance in the other part of the space. It is the same concept there, that you are basically creating disturbances that are extended in space. But as you get extended into space, obviously this electric and magnetic fields decay as you go farther from the charge. Same thing with light. As you go farther from the source, if you are very far from the traffic light, right, it doesn't look as intense. But if you come closer, it looks more bright, more intense, right? So intensity of light, which is nothing but the square of electric field, which we will see later, is also decreasing as you go forth. But everything is not great with Huygens principle because it ignores diffraction, for example. So if you place a slit, then a ray of light coming from a light source O, but this is the ray of light, this is a spherical wavefront, it propagates all the way up to the slit SS prime, but once it reaches SS prime, right, if you draw the secondary wavelets from the wavefront at SS prime, that is this, you see that this point at the top or this point at the bottom would inevitably produce wavelets that are beyond point P here. This is point P. So you see that there are wavelets beyond point P. Similarly, you see wavelets that are beyond point P prime. So light encroaches into the geometrical shadow of the slit SS prime, right? So so diffraction is encroachment of light into geometrical shadow. We will discuss diffraction later in great detail when we talk about interference. But here, Huygens principle proposes that basically the wavefronts end abruptly here. They just go this way. The reason is, if you want to really see that light is indeed encroaching into the geometrical shadow, if you want to observe diffraction, you won't be able to see it so clearly unless the wavelength of light is comparable to the slit width, right? If, for example, the slit is centimeters wide and you're using, say, a red color laser, which is roughly 650 nanometers, the slit is too wide compared to the wavelength, right? So you won't observe diffraction. But if you make the slit few, like maybe zero point 0.1 microns or so, you would be able to definitely see, or even 0.5 microns, you would be definitely be able to see the diffraction pattern, right? So that's where Huygens principle is flawed in a way, in the sense that it asks you to abruptly cut off the wavelets after P prime or P. But in reality, if you consider the wavelets beyond point P or point P prime, you would be able to explain diffraction, right? So now let's go to another principle, right? That is law of reflection. I'm sure all of you are familiar with the law of reflection. So if you consider a ray of light striking a mirror, so let's say this is the mirror, and if the incident ray is striking at an angle theta I, note that this angle is measured with respect to a normal. So we draw a perpendicular to the interface or the mirror here. So this is the plane in which mirror resides. So I'm drawing a perpendicular with respect to that plane, and I measure this angle theta I with respect to that surface normal. So if I have an incident and a reflected ray, the law of reflection states that this incident angle or angle of incidence is equal to angle of reflection. And a plane that contains the incident ray, the surface normal, and the reflected ray is called the plane of incidence, right? So the law of reflection is quite simple. Theta I is equal to theta R, incident angle is equal to reflected angle. And it is verifiable experimentally. So you can take, now you have, for example, if you go to Walmart, you can pick up maybe a small laser keychain for maybe a couple of bucks, and then you can bring it. You have to be really careful with it. Don't look directly into it and things like that, whatever instructions I mentioned. And you can verify experimentally for yourself that theta I is equal to theta R, right? Angle of incidence is equal to angle of reflection. But the question is, we are able to observe it experimentally. That's not where physics ends. We observed it experimentally that the angle of incidence is equal to angle of reflection. After observing it qualitatively, we have come up with a notation. We said, let's denote angle of incidence as theta I and angle of reflection as theta R, and then we are writing it down as theta I is equal to theta R. So this is the imperiometric form, right? This is the imperiometric that we talked about. So we are expressing it as an equation now. But this does not in any which way explain why theta I is equal to theta R. Right? It's something that you observed, and all that I'm doing is writing it mathematically. I'm not giving you any fundamental reason, any rationale about why should theta I be equal to theta R. And as physics students, this is what we are supposed to do. We are supposed to investigate why theta I should be equal to theta R. Why can't theta I be greater than theta R, or theta R be greater than theta I? Why should they be equal? Right? So if you think about it, we will get to that. Before we go there, let's reflect a little more on reflection. So you know that when you stand in front of a mirror, right and left are interchanged, right? And because right and left are interchanged, it appears our eye and brain interface interprets it as if there is a person standing behind the mirror, right? It's something what we call as a virtual image versus a real image, which we will again talk later in this chapter. But you see right as left and left as right in a mirror, right? Okay. So now another application of this simple reflection is those fingerprinting sensors. If you have used a fingerprinting sensor, right, you can see that it has a prism or some glass of some kind where you place your fingers, and then after some time your fingerprints are captured, right? So here you place your fingers on the prism, and if you zoom in into this area, you would see, if you zoom in into this area, you would see that your fingerprints have basically ridges and valleys. So this is a ridge and this is a valley, right? Those are the gaps. And if I shine a light, which could be an LED, which could be a small laser, and if I shine that light through the prism onto onto this fingerprint area, then wherever there is a ridge, light gets reflected, and wherever there is a valley, light escapes, right? Because this is just air, right? So based on how it gets reflected, you can capture that reflection with the camera, with the digital camera, and from there you can see the fingerprint, right? And once you have the fingerprint, you can convert that this into ones and zeros, right? 10010, right? Digital information. Once it is converted into digital information, you are basically going to be plugged into the matrix. No, I am just kidding. Just kidding. Okay, so that's how a simple reflection can be used to capture fingerprints. That's one application. However, I should also note that these fingerprint sensors using optical technology are a little bit bulky, so they're figuring out newer ways, like for example on your smartphones, more capacitive and other kinds of sensors are coming up, right? So, okay, so now let's go back and see why theta I should be equal to theta R, right? So, to do this, let's first see what's Fermat's principle. Basically, Fermat's principle states that if you have multiple paths available to you, light takes the path which requires the shortest time. Now, that's why this is also called Fermat's principle of least time. It is not shortest distance, it is shortest time. If you are in the same medium, say if you are in the same medium like air, and you're going from point A to point B in the same medium, because the velocity of light doesn't change within the medium, shortest time and shortest distance may be equal. But if you are changing the speed of light, for example, if you are going from air into water or into glass, you change the speed of light. In that case, least time is not necessarily the same as least distance. That's why it is very important to note that Fermat's principle is a principle of least time, not least distance. In any case, it states that light would take a path that requires the shortest time. So now our question is, we have point A, we want to go to point B. If there is no other constraint, the path I would take is if point A and point B are in the same medium and there's nothing in between, I would just take a straight line, right? So in a given medium, light travels in a straight line. You know this. That basically comes from principle of least time. Now, what we would like to see is, I want light to go from A to B, but I am adding an extra constraint. I want to reflect it off mirror mm prime. This is the mirror mm prime. So if I have to go directly from point A to point B, I would just take a straight line. But if I have to go through the mirror, if I have to strike the mirror and go, that is, we're looking at how reflection works. Then how does it work? So let's take a look at that. So Here, if I want to go from point A to point B after reflecting off of mirror mm prime, I want to take the shortest time possible. So let's say I go directly from A to this point called D. Then I go from A to D very fast because it's right below A, but D to B is very long, right? If I move this point D slightly to the right, and instead of going directly down, if I go from A to E and I reflect off from EB, I am traveling a little longer from A to E compared to A to D, but I save a lot more going from E to B. I can keep drawing these different curves and figure out which would take the least time. But we can also do another thing, that is, I can look at the reflection of point B. I can look at the reflection of point B at below the mirror, and I can see what would be the least distance to go from A to that reflection B prime. So as you can clearly see, we are going from A to B through this point C. That's the least path that requires the least time, right? So here this is a hypothetical point B prime. We are not looking at the real point B prime. We are looking at a hypothetical point B prime. So this would be the shortest path. So that's how light is going to go. So it's going to go here and then go there. And looking at the geometry, right, this distance, if this is x, this is also going to be x. This is a right angle, this is a right angle. So you can see that the triangle here is the same as the triangle up here. So now if I were to look at theta I, right, if this is theta I, right, then you can see that whatever this angle is should be equal to theta I because of the principle of least action. So least time, theta I is equal to theta R. In another way, if you go back to this, we can plot a graph where we have the amount of time it takes and where we are striking the mirror mm prime. If I strike the mirror mm prime at point D to begin with and go to B, it takes a long time. So if I strike the mirror at point D, time taken is somewhere here. If I strike the mirror at E, I take a little lower time. So my time is here. And so on and so forth. If I strike the mirror at F, this is C, and at different points, right, you can see that it goes like that. And so the least time would be at C. So that's the path that light takes. So if I go through C, it would take the least time going from A to B. And that's the path that light chooses. And that's why we have theta I is equal to theta R. But although we explained how theta I is equal to theta R from Fermat's principle, we didn't really explain it, because is light trying out all these different paths? Is, like, for example, if we go to this graph, is light drawing a plot like this, checking all the paths out, and somehow going through C? It is not very easy to understand why Fermat's principle of least time should be working. We have explained theta I is equal to theta R in terms of another principle of least time, but we also need to explain why Fermat's principle of least time is valid, right? So although it is outside the scope of this course, you can read Feynman's lectures. You can read Feynman's lectures on quantum electrodynamics. We'll try to cover that later. So basically, we call this as path integrals. Each path you can give a certain amplitude, and you can denote the time it takes. If the time it takes is t to go from one path to another path, you can give each point an amplitude. We have already used a, so let me use another letter. So let's say alpha e to the power it. So you give each path some weightage like alpha, and e to the power it. T is the time it requires to go from to complete, to go through that path, right? And then you look at all these things, and from that basically you can figure out that Fermat's principle states that light takes the path which requires the least time. But we'll not get into that. We'll stop at Fermat's least principle, and look at another law, that is the law of refraction. So if you have refraction, unlike reflection, so let's say I have an interface here. Let's say this point is A. I have a ray of light coming here, right? And it is getting refracted here. So let's say my ray of light begins from P and ends at P prime, right? And let's say this distance is X and this height is H. Let's say this is Z prime and this is Z. Okay, and so now here we want to look at the angles, right? So we want to look at the incident ray. This is the incident, right? So we would like to look at the angle of refraction theta prime and the angle of incidence theta I, right? So now in case of refraction, you are going from a medium of one refractive index to a medium of another refractive index, from n to n prime. So we're changing the speed of light as we go from one medium to another medium. So it is not as easy as reflection, because in case of reflection, you're still in the same medium. We're not considering a ray of light that is getting transmitted into the glass. So you're only considering everything in the same medium. So principle of short time is very simple there. But here we have two different media. So to calculate the total amount of time, let's see, I need to go from P to A. So first let me calculate the length P to A, length of P to A. That would be simply this hypotenuse. So here the opposite side is X, this side is Z. So that length is simply X square plus Z square. Similarly, length of AP prime would be, this height is H, but I have to knock off X from it, this height. So I would get H minus X here, and this is Z prime. So I would have H minus X square plus Z prime square. So in this medium, the velocity of light is C by N, and then this medium, velocity of light is C by N prime. Right? We always divide the velocity of light by refractive index, and because the fastest thing is light, the refractive index is always greater than 1. Or greater than or equal to 1. So if you do happen to find a material that has a refractive index lower than 1, please do email me or call me, no matter what the time is, and then we'll write up the paper together, and I'll let you share the Nobel Prize with me. Okay, jokes apart, now we figured out the length and we know the velocity, so we can compute the time. So the time that it spends in this medium here, the incident ray spends in the medium of refractive index n, would be the length, that is X square plus Z square, by the velocity, which is C by N. So I can write it as N times square root of X square plus Z square divided by C, right? Similarly, this time T prime would be the length there, which is square root under H minus X square plus Z prime square divided by C by N prime, right? Or I can write, instead of writing N prime here, I'm writing N prime there. So T prime would be N prime h minus x squared plus z prime squared by c. So the total time then, total time for going from p to p prime, we are finding the total time so we can minimize it and figure out a law for refraction. So that would be equal to n x squared plus z squared plus n prime square root under h minus x squared plus c prime square divided by c, right? So to minimize this, the variable here is at what angle does my ray strike the interface, at what angle. So if I move this, right, if I move this, for example, if I make it like this, right, or if I change this, how is it going to be refracted? That's what we want to figure out, or we want to figure out a relationship between theta incident or theta and theta prime. Just like how we figured that theta I is equal to theta r, we want to come up with a similar expression for refraction. Now we have the total time for refraction, right? So total time we saw as n times square root under x squared plus z squared plus n prime times h minus x squared plus z prime square divided by c. And this c is, you can ignore it because it's just a constant, right? And to get the total time here, the variable that we have is x. So we differentiate this total time with x. We take the partial derivative and set it to 0. And if we do that, you basically get this law that n sine theta minus n prime sine prime is equal to the 0, right? So sine theta is x by x square plus c square, right? So x is the opposite side, and the hypotenuse is x prime z prime square, right? The result is known as Snell's law or law of refraction. Here we derive the law of refraction using Fermat's principle. But in the textbook, in Pedrotti and Pedrotti, there is a section where Snell's law is derived from Huygens principle. It is very similar, but nevertheless, I would like you to go through it because it's already in the textbook. We just derived it in a different way using Fermat's principle of least time. Okay, so now let's think about Snell's law as a minimum time principle. So this is an example given by Feynman. So Feynman says that imagine that you have a beautiful girl or a beautiful man falling out from a boat into the ocean, and you see them, you're on the beach, you want to save them, right? You want to save that person. So you want to get there as fast as possible, right? So you know that you can run faster than you can swim. So then in that case, you would like to maximize the distance that you can travel on land. You can run on land. For example, if this person, if you're standing here, if you run like here, and then if you try to swim, you have to swim a longer distance than you run, right? And same thing, if I go here, I can run, but then I have to swim a longer distance, right? And if you see that there is this distance is the longest distance I can run, and here I can swim. So I reduce the distance I have to swim. But the same thing for light. Light can travel faster in air. For example, if this is air and this is glass or even water, light can travel faster in air than in glass. So to go from one point to another point, light is basically using the same principle as what we have discussed here. It is running as far as it can go on land, and then it is using basically then it is basically reducing the distance it has to swim. I hope I came across in what I was trying to explain. Right. So that's Snell's law is in a way the least time principle. Right. Now let's discuss two types of refraction. One type of refraction, you are going from a less dense medium to a more dense medium. So it is like going from air to glass. This is what we have been discussing, right? So in air, roughly the speed of light is same as it is in vacuum, so n is almost equal to 1. In glass or in water, it is higher, so 1.5. So if you go from air to glass, or if you go from a less dense medium to a denser medium, then the angle with respect to normal decreases. So this is the interface here. This is the air glass interface, right? So it is extending into the screen. So when you draw a normal, the perpendicular that you want to draw to this interface is this way, right? And so if this ray of light is incident here, this is a larger angle, and if I am going from a less dense medium to a higher dense medium, this larger angle decreases. If I flip the other way around, if I am going from a denser medium into a less dense medium, for example from glass to air, then it increases. So here the angle with respect to normal is theta, and here it is theta prime, which is basically higher or larger, right? So now we can consider a case where my refracted ray basically goes along the interface. We know that Snell's law states that n sine theta is equal to n prime sine theta prime. So I want to consider a situation where I am going this way, but my theta prime is 90 degrees. That is, my ray of light goes just this way, right? So I want to consider a special case where my ray of light is going in at an angle theta, but is completely refracted along this interface. Right? We know that Snell's law states that n sine theta is equal to n prime sine theta prime. So I want to figure out at what theta would I get at theta prime is equal to 90 degrees. Right? So we'll do that in a minute, but before we do that, that particular angle where the refracted ray lies along the boundary is called the critical angle. It is the critical angle. So when the angle of incidence is exactly equal to the critical angle, so when the angle of incidence, when this angle is the critical angle, then the refracted ray lies along the boundary. So this is the incident ray and this is the refracted ray. So this is incident and this is refracted. So when theta c is exactly the critical angle, the refracted ray is at 90 degrees. So let's see, we know that n sine theta is equal to n prime sine theta prime. This is coming from Fermat's principle of least time, and which leads to Snell's law, as we have seen, and we're using Snell's law to see when would theta prime be equal to 90 degrees. And if I set theta prime is equal to 90 degrees, then I have simply n prime, because sine 90 is equal to 1. And so I can see sine theta would be n prime by n, or theta, or this is the critical angle. Critical angle is sine inverse n prime by n. Right? So you can see that critical angle is given as sine n prime by n. Okay. So now let's do a simple problem. So here we would like to figure out what is the critical angle of diamond air boundary, right? So here we have diamond air boundary. So in air, the refractive index of air is roughly 1, right? And refractive index of diamond is around 2.42. So we have seen that the critical angle is sine inverse of n by n prime Note that if you are going from diamond to air, you cannot have a critical angle because diamond would have a refractive index of 2.42, right? It's a denser medium, right? So there you increase the angle of refraction with respect to normal as you're going from a less dense medium to denser medium, right? Or sine inverse 2.42 does not exist, right? So this happens when I'm going from air to diamond, right? Um, so n air by n diamond, so n sine inverse 1 over 2.42, which comes out to be roughly 24 degrees, right? So the angle, the critical angle is is this 24 degrees. Now, if you are above the critical angle, right? So critical angle is if I'm going from here to there, if I'm going here to there, at critical angle, I basically refract along the interface. But if I go more than the critical angle, if my angle of incidence is greater than theta c, then basically this doesn't get refracted, it just gets back into the medium, right? So this is what we call as total internal reflection. I think when I was explaining how the critical angle doesn't work from A to diamond, I think I said diamond to A or something like that. So beware of that. When you are going from so let's look at this equation, right? So if you have n prime by n, right? If n prime is greater than n, right? Then basically this fraction would be greater than 1, so sine inverse does not exist. This sine inverse exists only if n prime is less than n, right? So just bear that in mind, right? So here it is going from a medium of n to n prime. So it will only get refracted, or it would only get go at a critical angle when that happens, right? So bear that in mind. Okay, now you have seen sparking diamonds. So in case of diamonds, if you have a ray of light entering the diamond, because the critical angle for diamond is 24 degrees, right? If you enter the diamond at any angle, pretty much almost all the angles, right? If you cut the diamond in such a way that many of the rays that are entering the diamond can be completely internally reflected, right? Then you will see that the diamond sparkles a lot. If you cut the diamond a little differently, then so if this cut is not proper, for example, then instead of getting total internal reflection, this ray of light would just go out. If you cut the diamond properly, right, then it would get total internal reflection, and then that's where you see like the diamond is filled with light, it is sparkling, right? So that's the importance of the cut. So now let's look at total internal reflection. So total internal reflection, again, as I said, happens beyond the when you're going from glass to air. Total internal reflection happens when your angle of incidence is greater than the critical angle, right? So that's where you get an evanescent wave. An evanescent wave meaning not all the light is completely reflected. Some of the light escapes and it goes into air. That's called an evanescent wave, right? This is the electric field as a function of distance above the interface. So it decays a little bit, right? So this is called an evanescent wave. So a little bit of light goes out. So this evanescent wave is often used in different optical spectroscopy tools. One is ATR, attenuated total reflection infrared spectroscopy, right? Okay, so that's about evanescent waves. Another thing about principle of least time is principle of reciprocity. So principle of reciprocity means that if I go from A to B, if I have a light source at A and I have a detector at B, then the shortest distance, if this is a straight line, and if I change the position of the light source and the detector, instead of putting the detector at B, if I put the detector at A and the light source at B, it still is the same path. It's still a straight line. So if light goes from one way, it can be sent other way too. That is the principle of reciprocity, right? This is when we study wave equations, you will see that this would be called the time reversal symmetry in case of Maxwell's equations. And when we see Maxwell's equations, you will see that this principle of reciprocity jumps out at you. So in fact, later during the course, I will share a paper that my group published in, I suppose, 2011, a paper in 2011 and a paper recently, 2 years back, maybe 2017, where we showed, where we basically broke the principle of reciprocity in a way. We showed, for the first time, we showed non-reciprocal transmission of light. Non-reciprocal transmission of light. We call that photonic diode. But it's a little more complicated to discuss that at this point. That has to do a lot with nonlinear optics, which we might get into later in the course. But basically, principle of reciprocity is a consequence of principle of least time. So let's quickly end with converging and diverging lenses, and then we will discuss rest of chapter 2 in the next lecture. So now let's see, if I have a lens that is like this, right, that is made of glass, and if I have rays of light coming here, right, now let's say this is ray A, ray B, and ray C, right. So ray A would spend very less time in glass inside the lens, right, compared to say ray B. So because ray A gets out of this very fast, it would have this ray would have reached much farther compared to this ray at a given time, because this ray had to spend longer time inside the glass. And similarly, C also would go out like A, right? So a parallel beam of light entering this lens would become like this, right? And if you go far enough, it would converge to a point, right? And you can see this C here, right? So this C sort of is a mnemonic for converging. Now instead of this, if I make concave lens like this, instead of convex, if I make concave, and if I have same parallel beam coming out, A, B, C, A would travel a longer distance, right? So it would go here. B has to, on the other hand, travel the shortest distance, so it would be farther, and C same as A here. So now you see that this is like D or diverging, right? So one is a converging lens, another is a diverging lens. Right? Just by looking at how long it takes the light to go through a given portion of the lens. So initially you have parallel rays, but depending upon the shape of the lens, you can either converge it or diverge it, right? So those are the converging and diverging lenses. And finally, let's just look at a parabolic mirror. So in case of parabolic mirror, again, you apply Fermat's principle here. So for example, in astronomy, if you want to look at a star which is very far away, right, light years away, let's say, and you want to focus this light to a given point, and because the star is very far away, the rays of light that are coming to us, you can consider it as if they're coming from a light source that is infinite distance away. So they look like parallel rays. So that's why these rays are parallel here. So now we want to focus this to a single point. So then you can see that the shape of the mirror that you want to choose should be parabolic, because if you look at this ray AA prime, right, if it hits here, it goes there, right, and same thing here. So irrespective of where the rays hit, you want to make sure that you have a mirror such that this distance A prime A double prime is equal to this distance A prime P prime. Similarly, you want to make sure that this distance, say x double prime or x prime x double prime, is equal to x prime p prime. So the only curve that satisfies all these relationships, if I write them out for B, C, D, so on and so forth, is a parabola. So if you have a parabolic mirror, then it would converge all this light to a point P. So that's why these kind of mirrors are often used to focus light. So you can Google parabolic mirrors and you can see huge parabolic mirrors that are often used in observatories. Okay, so we'll stop here for this lecture, and we'll continue later in lecture 4 on chapter 2. Thank you.